Bam! Mr. True. In this math lesson, we're going to be taking a look at question 6 of the 2018 Calculus A/B test. It's going to involve some slope field sketching. It's going to involve some linear approximation, and then finally solving a differential equation, a separable differential equation. So let's see what we got going on here. Consider the differential equation of dy dx is equal to 1/3 x times y minus 2 squared. Part A says, sketch the solution curve that passes through the point 0, 2 and the one that passes through the point 1, 0. And I've done my best to approximate what that slope field looks like. By the way, in the description you will find timestamps to let you jump ahead to each of the three parts. You'll also find a link to the AP College Board website where you can download the PDF of all of the questions, the scoring guidelines, the scoring commentary, all that good stuff. Great resource. So let's try and get that 5 on our AP test. When you look at the slope field, you want to make sure that you sketch a solution curve that goes all the way through the slope field, passes through the 1, or in this case 2 points that they're indicating, and you kind of just look through here and get the general gist of what that graph looks like. In other words, you know, we don't want to look at this point of 1, 0 and say, oh, well, the slope is positive, maybe a slope of positive 1, and then just draw a straight line going through that point. Because if you were to draw a straight line, at some point you'll get down over here and you're like, man, my graph is going down, but the slope field is showing, or, well, my graph is going up, but my slope field is showing that the slopes are negative. You kind of want to the best of your ability, just kind of go with the flow of that slope field. Like here at 0 and 2, through this point, that slope is horizontal. And as I extend horizontally, I end up hitting more little blue marks which represent the slope of the solution curve at that particular point. And we just keep hitting slopes that, well, appear to stay horizontal. So you can put arrows on this, which is never a bad idea, or just let that curve run right off the edge of the slope field. If you stop this short and make it look like a line segment, you will lose that point. At this point of 1, 0, we see a slope that appears to maybe have a slope of 1, and as we go up and up and up, well, we're not going to go up at that same constant slope forever, because it seems like this sort of curves down. And even to the best of my ability here, so I'm trying to draw this slope field, even as I get to this next column with tick marks, if I were to make a linear function, I'm already looking like I have a steeper slope than what's indicated by the slope field. So you want to kind of just curve that over, go to the end, and or include an arrow at the end of that. As we cross through the x value of 0, all of these slopes, regardless of what the y coordinate is equal to, are 0, or these are all horizontal tick marks. So we're going to come through this point and level off and kind of come through horizontally through the y-axis where x is equal to 0. And as we come to the other side, we see that the slopes, now I'm kind of drawing this from right to left, which isn't really how the flow of the graph works, right? These slopes over here seem to start off being either nearly 0 or quite negative, depending where you are vertically along your slope field. But if I match over to this other side, it kind of seems like the slopes are maybe even a little bit positive here, but they start to fall down. I think that's probably just my poor drawing. They start to fall down, come to the y-axis, and then rise back up again. So something like this would be your two approximations of the slope field, of the solution curve going through the slope field. Make sure you, of course, pass through the point of 0, 2. Make sure you pass through the point of 1, 0, or whatever they happen to give you for this particular test or any question with the slope field, and just follow along as best you can. If you're a little bit off, we're not going to be concerned about that, just not wildly off. You can't, again, have something coming down here with a positive slope, or clearly in this entire quadrant 3, all those slopes are negative, and you'll be good. Now, part B says, let y equal f of x be the particular solution to the given differential equation with the initial condition of f of 1 is equal to 0. So we're talking about a solution that passes to the point of 1, 0. Basically, maybe we're looking at this curve down here. Write an equation for the tangent line to the graph of y is equal to f of x. So if I have done a reasonable job of drawing my solution curve, then we're talking about a tangent, a line tangent to this graph, y is equal to f of x at x equals 1. So we're going to find the equation of a tangent line that looks something, maybe something like this. You know, my sketch through the slope field is just that, a rough sketch, but somewhere along that. And we're going to use the equation of the linear tangent line to approximate the function's value at 0.7. So we know, given this initial condition of the solution curve goes through the point of 1, 0, we know that this is exact. The rest of this is just a sketch. But we're going to estimate the value of this orange solution curve at the value of 0.07. And the tangent line can actually be a good approximation for any curve as long as you're close to that point of tangency. Let's go ahead and 0.07, or excuse me, 0.7 is close to that x value of 7. So let's take this off so I have some room to work and find the equation of that tangent line, or the line tangent to f of x at x equals 1. Okay, so we're looking at, first we need slope, right? What do you need to write the equation of a line? A point and a slope. Well, we have the point, it's 1, 0. We need the slope. So dy dx at the point, and this derivative is asking for both the x and y coordinate. So at the point of 1, 0 is equal to 1/3 our x value of 1 times our y value of 0 minus 2 squared. So, okay, so negative 2 squared is 4. 4 times 1, 4 times 1/3. So we have a slope of 4/3. So the equation of our tangent line is in point slope form. Y minus y sub 1 is equal to m 4/3 times x minus x sub 1. Now don't please be too quick to put this equation of a tangent line into slope-intercept form, which is actually the form that's most commonly requested. If you give an equation of a tangent line as a final answer, if a AP question is asking for an equation of a tangent line, they are going to want that in slope-intercept form. But you really want to leave this in point-slope form to make it a little bit clearer as to how you're going to find that approximation at the x value of 0.07. At least the way I like to look at this. So we are looking at y is equal to 4/3 times 0.7 minus 1. And at least in terms of doing linear approximations, I like my tangent line to be in point-slope form as opposed to slope-intercept form that you would be giving for a final form of a tangent line. Now, this 7/10 is best worked with in terms of a fraction, so we're looking at 7/10 minus 10 over 10. Now we're looking at 4/3 times negative 3 over 10, and the 3's are going to cancel out. The 4 and the 10 are going to cancel out to be 2 and 5. So our final answer here is that our approximation is at negative 2/5. So now this is the value that we're getting from our tangent line. It's just an approximation for that f of x function. And I think it's probably a good idea, since we're being asked to estimate the value of f of 0.7, that therefore f of 0.7 is approximately equal to negative 2/5. And if you want to see how the points are divvied up again, find that link to the AP College Board website where you can download the scoring guideline and see where the points are divvied up. You can also look at the master scores comments to find out where students most commonly made their mistakes as they were working out this particular and all the particular problems on the AP test. Part C coming up right now. And for the last part, C, we're going to find the particular solution to the differential equation, the separable differential equation using that initial condition of f of 1 is equal to 0. So this is our solving separable differential equations. My students would have seen this in chapter 6 of our Larson book. So it's the only type of differential equation we need to worry about solving in calculus AB, or BC for that matter. How are we going to separate these variables? Well, we're going to move things around with multiplication and division. We're going to bring the dx over with an apparent multiplication and bring the y minus 2 squared over to the left-hand side, giving us 1 over y minus 2 squared dy is equal to 1/3 dx. Now that we have these variables separated, everything in terms of y on the left, terms of x on the right, we're going to set up an integral on both sides. I'm also going to bring this y minus 2 up to have a negative power. So we're going to be integrating y minus 2 squared dy. I'm also going to bring this coefficient of 1/3 out front, this constant multiplication of 1/3 out front, and we're going to be integrating x with respect to x. Okay, well, the right-hand side is quite straightforward. Actually, both of them are. But on the right-hand side, it's just simply x. We're going to raise that power by 1 and divide by that raised power. So we're going to have 1/3 times x squared times 1/2, because we're going to divide by that increased power. We're going to have a plus c on the right-hand side. No need to do a plus c on both sides of differential equations as you're solving them. On the left, you have two choices. You can take this y minus 2 and square it, make it 3 terms, integrate each of those 3 terms with basically the power rule individually, or you can complete the chain rule pattern, or maybe that chain rule pattern is already completed. That's going to allow you to have fewer terms. It's going to allow you to have y in only 1 term instead of 2. You have a choice here, not saving maybe necessarily a tremendous amount of time. Oh, that should be negative 2. But I'm starting to get comfortable and realizing how even just a little bit of time saving some part of an AP question, a timed test, how beneficial that can be. And if you look in here and you say, well, let's let u equal y minus 2, well then u prime would be just simply 1. And we already have a multiplication of 1 or a factor of 1 out here, but if you want to see that as a addition, not an addition, but in introducing that factor of 1, you can divide by that factor of 1 if you like. Nothing's really going to happen here, but if that was like a 2y, then you would need to introduce a multiplication of 2 to complete that chain rule where you have a u and a u prime, and if you introduce a multiplication of 2, you need to balance it with the division of 2. So we're going to integrate y minus 2 to the negative 2 power. If this had no power on it, or if it was a power of negative 1, then the result of our integration would look like a natural log, it would be a natural log function. Some of my students that maybe struggling a little bit might make that common mistake. But we're going to raise this power by 1 and then divide by that increased power. And at this point, we're going to remember that you're going to save yourself the most amount of time with these problems usually if right after you finish the integration, you go ahead and plug in that x and y coordinate to help you solve for c. Don't clean this necessarily up for y first and then find out what c is equal to. So our y value is 0, our x value is 1, and so we're looking at, what do we have here? 1 divided by negative 2, so we have 1/2 times, and we're going to, this is multiplied by 1, so we're just going to take this this positive 1/6 and subtract it over to the other side. Find a common denominator and find out that C is equal to 2/6, or that C is equal to 1/3. Now, that means that we're ready to go ahead and finish writing up a cleaned up version, making a cleaned up version of this differential equation. So we have -1 over y minus 2 is equal to 1/6 x squared is equal to 1/3, not equal to, but plus 1/3. And they're not generally happy until you get an equation that is solved for y. So we're going to, let's see here, what might be the best way to do this? How about we multiply both sides by 6. So we have -6 over y minus 2 is equal to x squared plus 2 as that gets distributed. We're going to multiply both sides by y minus 2, and actually at the same time we're going to divide both sides of the equation by x squared plus 2, and then finally add both sides by 2. They are not generally happy with your final answer when you're solving separable differential equations until you get y by itself. Sometimes it's okay to get like a y squared or y cubed by itself. And, you know, the math is getting a little bit tough. Of course, this is an AP Calculus test. We should be expected to do some fairly complex algebra. But don't doubt yourself as you're doing this, because maybe you think, oh, well, wait, what's going on here with this y minus 2 in the denominator? That seems a little bit funny, and the right-hand side's a bit complex. Just have confidence in what you've done, the skills that you have, as I check my answer, but we are good. And just keep going through that problem, and then when you have time, if you have time at the end of your test, go back and look over your work for the questions that you're maybe a little bit unsure of. But don't start doubting yourself because the algebra looks a little bit maybe complicated or funny or unexpected. They're trying to really make sure you know your concepts and you're confident in your work. So that is number 6 of 2018 Calculus AB. I'm Mr. Tarrou. Bam! Go to your homework and get a 5 on that AP test.